This next section is one of the most interesting and exciting sections, I think, in the entire physics course. This section here, 37.4, in this section we will discuss the relativistic energy equation. And we will really derive some interesting things here. Remember, there's an old equation for our kinetic energy, or the energy of motion, and it's 1/2 mv squared. This is Newton version of the kinetic energy. We've used it all semester, and of course it's valid anywhere, below 1/10 of the speed of light. It tells us that if an object of mass m moves with velocity v, we have a kinetic energy. If the velocity drops to 0, there's no kinetic energy at all. Now you will recall that P is equal to mv, and therefore we can write this kinetic energy as multiplying the numerator and denominator by an m. We can write this as the kinetic energy as mv divided by 2m, where I've added an m here, 2m on the bottom, and I've put another v up here, so it's m squared v squared. That this is the same as saying that the kinetic energy is equal to p over 2m, where p squared over 2m, where p, the momentum, is mv. Okay, this is Newton. And this equation is very important because it relates the energy, and I'm just going to call this the energy now, relates energy to momentum and to mass. Now we can ask the question, how are energy, momentum, and mass related in relativity? And the equation for that, which I'm not going to derive for you, it's a little bit too advanced, is a little bit more complex. It says the energy divided by the speed of light squared, E over c squared, minus p vector squared, the momentum squared, is equal to m squared c squared. This is Einstein. That takes a little bit of work to show how this is related to this, but you see that again we have energy, momentum, and mass related, but we also have an equation for the speed of light. Let's look at the consequences of this equation. First one I want to look at is to use this equation, I want to solve for the energy. So we're going to do that, and we're going to get E squared is equal to, now there's a c squared here that multiplies both of these, c squared p squared, which I bring to the right-hand side of the equation, plus m squared, and now it's c to the 4th because I've multiplied through by c squared. And therefore the energy is equal to the square root of c squared p squared plus m squared c to the 4th. Okay, it looks quite different from this equation up here. But let's see how this actually relates. Well, first of all, the first example I want to take, number 1, is I want to take an example where the particle is sitting still. If it's sitting still, it has no momentum. So I'm going to take v is equal to 0, which implies that p is equal to 0. No velocity, there's no momentum. If that's true, then E is equal to the square root of m squared c to the 4th, which is the same thing as saying E is equal to mc squared. Probably the most famous equation in all of physics that relates energy to the mass of a particle, and it says that even if a particle is sitting still, it has what is called a rest energy, equal to mc squared. It also implies that energy and mass can be converted into one another. In classical physics, energy is conserved and mass is conserved. But in relativity, this is not true. These two things mix up, and we can take pure energy and make matter out of them. We can take matter and annihilate it and make energy out of it. This is our result number 1. Incredibly important. And you'll recall that even 1 kilogram converted to pure energy would give us how much? The energy of 1 kilogram would equal to 1 times c squared, which is 1 times 3 times 10 to the 8th meters per second squared, which would be 9 e to the 8 and 8, 16. That's a 9 with 16 zeros after it, and that's in joules. Unbelievable amount of energy can come from a small amount. This is just 2.2 pounds. So this is an incredible result. And of course, it's the foundation of atomic theory, particle physics, and it's been totally confirmed a trillion times. Well, now that we've done that, I want to go back and point out something that we missed. We made a slight mistake when we wrote this equation. We said when we took the square root of both sides that E was equal to this. But actually, E is equal to plus or minus the square root. When this first occurred, everyone threw the negative sign away. But later on, about the year 1925, when physicists were dealing with relativity and quantum theory, it was determined that even if you threw the negative energy away as having no meaning, it came back into the equations. So one physicist, Paul Dirac, who later got the Nobel Prize for this, said he forwarded the idea that negative energy was real, and for every piece of matter there was another kind of matter that had not positive energy but negative energy. He called this antimatter. This antimatter, for a given mass, would have an energy E is equal to mc squared. And also, for that matter, there would be a negative energy type of object, and it would be, whereas this would be called the matter, this would be called the antimatter. When the matter and the antimatter come together, they annihilate and make pure energy. Well, people laughed at this for about a year. And then they finally did the experiment, proved that an electron had another component, a positron, that did have negative energy. They annihilated one another and went out in a flash of pure light. So when an electron, negative charge, met up with a positron, the antimatter for the electron, they produced 2 photons of light and disappeared. An incredible equation. So not only do we predict E is equal to mc squared, by taking into account the plus or minus sign, we get something else. We get the prediction of antimatter. Like I say here, the negative sign was ignored for about 20 years, and we talk about that annihilation. Now we're going to solve this other equation and solve for mass. How do we do that? Well, we're going to take the same equation, and I'm going to now take a new type of unit. I'm going to imagine that light goes in a distance of a new meter. This is a new meter in 1 second. If it goes a meter in a second, then the speed of light, c, is equal to 1, and it lets us write this equation in a simpler way. Namely, it lets us write m squared is equal to e squared minus p squared. And that's just in this set of units. It's a very long meter. It's 186,000 miles long, but that doesn't matter. Now I want to solve for m, and I get m is equal to the square root of e squared minus p squared. And whereas this was our second result here, our third result is now, is there something called negative mass? Well, it has never been found. We don't know if this exists or not. But if we had negative mass, you'll recall that the gravitational force, which is g m1 m2 over r squared, this is attractive. If one of these had a negative mass, it would be repulsive. And therefore you would have an object that on the face of the earth would fall upward, going faster and faster and faster if it had negative mass. We wondered for a while around the 1950s if antimatter might have negative mass. And it was then proved for antineutrons that they also fall in a gravitational field. So far, we still do not know if there's anything in the universe that has negative mass. Now, looking back at this equation again, we have, anytime we have a binomial equation like this, or square root of the difference of two terms, we ask ourselves, what are the possible states? Well, we can have E greater than P, E equal to P, and E less than P. If E is greater than P, this is just some number, positive, and we take the square root, and we're going to now assume that this is positive. So this is a regular piece of matter. Matter is real value, a number, and one can show that the velocity of this matter has to be always less than the speed of light. If the energy is equal to P, E is equal to P, then we find that the mass is zero. And these objects, like the photon, which is a perfect example, the piece of light itself, have to move at a speed of c, never slower, never faster. And finally, if E is less than P, then we get the square root of a negative number. And that, of course, tells us the mass is imaginary. It's like the square root of -1, or minus some other number. So mass is imaginary, and these objects, called tachyons, have a velocity that's always greater than the speed of light. Tachyons. Have these been found? Never. We don't know if they exist or do not. They are, of course, a lot of interesting work lately about the neutrino is that it might have versions that can go faster than the speed of light. But we have found both of these. In fact, not only is this true for the photon, that it has no mass, it's also true of the graviton, responsible for gravity. So this takes us through these main equations, and you can see here that I have covered all of these forms of E greater than P equals less than P and equal to P, and what these are called. We have never found two of these types. No mass less than zero, and no mass that's imaginary, where the velocity goes faster than the speed of light. Never found, but who knows, may be possible.